In this video, we're going to examine the kinematics of some wheeled mobile robots. So we're going to look in detail at the kinematics of the fixed standard wheel, and then we will examine an example using the fixed standard wheel on a robot chassis. So the differential drive robot. We'll examine the kinematics of that configuration. Whenever we talk about kinematics, this is the study of motion. So we're just looking at velocities, accelerations, and we're not considering actions like forces, inertia, etc. In robot kinematics, the field of manipulator kinematics is well established, and this figure shows an example of that. We have here a 3-revolute manipulator. We have 3 joints, and the position and orientation of the end effector is specifically determined by the values for the 3 joint angles. Now, it's a nonlinear equation, this function, relating the xy theta, or xy, the position and orientation of the end effector, has a nonlinear relationship to the joint angles, but it's straightforward to calculate because it's geometry and we know exactly the position and orientation given the joint angles. That's not so for a mobile robot. Just knowing the encoder values, so how far each wheel has moved, does not give you a unique position and orientation. So we don't have any direct position measurement in a mobile robot like we do in a manipulator. In order to estimate the position and orientation, we have to integrate these wheel displacements over time. Here's an example showing 2 paths, and each one has the same total offset for the 2 different wheels, and the same total offset or distance traveled by the origin of the robot frame. And yet, at the end of each path, the robot is in 2 totally different places. And it just depends on the order or the history of the wheel rotations. So in S1, the 2 wheels went together at the same speed for a while, and then the wheel on the right slowed down. Whereas on the second path, the wheel on the right went slower than the first one at first, and then they started going the same speed. So the total displacement of the wheels is the same, but they end up in a different location. So that's an illustration showing how mobile robot kinematics are different from manipulator kinematics. And the term that describes this difference is non-holonomic. This mobile robot is non-holonomic, and that technically means that it's subject to differential constraints. So in the robot manipulator, the position of each link is constrained by the position of each joint angle, or of each joint. But in the wheel mobile robot, the constraints are velocities. So the velocity is constrained by the geometry of the wheel. And so that's what's meant by the differential constraints. This figure shows a standard wheel. So we're here in the robot frame, and the point P is considered to be the origin of that frame. And relative to that origin, we have a wheel, a standard wheel, and it's at a distance L from the origin. And the contact point between that wheel and the ground is on the line L, or I'm sorry, it's a distance L from point P, and that line is at an angle alpha from the robot X axis. So that's how we locate the wheel. And then the wheel, if it's steerable, the steering angle is considered, or it's called beta, shown here. And if it's fixed, then that beta won't ever change. So all these parameters, alpha, beta, and L, locate the wheel relative to the robot frame. And then the wheel rotation angle is called phi. We use the letter phi to denote the wheel rotation. And finally, the angle theta has to do with the orientation of the robot chassis relative to an inertial or world frame. So that would be the angle between the world x-axis and the robot x-axis. and the world x-axis isn't shown here, but the angular velocity theta dot is pictured. So we can see here that phi is defined positive so that it's a positive angle, phi, a positive velocity speed, phi dot, gives a positive velocity in the x direction. So the question is, what constraints does this wheel impose on the chassis? So if we have a robot chassis with this wheel on it, what differential constraints, what constraints on the velocity does this wheel impose on the chassis? Give you a second to think about that. There are two of them. That's a hint. It imposes two velocity constraints. One of them is shown here in yellow. And that is that the velocity in the wheel plane direction, the velocity of the robot in this direction, is equal to the wheel radius times the wheel speed. So that's one constraint. So the robot velocity in this direction is related to the wheel speed and wheel radius. And then the other constraint is that the robot chassis velocity in the direction perpendicular to the wheel plane has to be zero, because we assume that the wheel isn't going to slide. This figure shows those velocities. So we have here the velocity in the wheel plane direction is equal to the radius times phi dot. And here we have the so we have the velocities in the coordinate frame. So we have x dot, y dot, and theta dot. So those are the velocities of the robot chassis in this robot coordinate frame. And we've decomposed those velocities into components that are in the direction of the wheel plane and perpendicular to the direction of the wheel plane. So x dot can be decomposed into x dot sine alpha plus beta. So that's the component of x dot that is in the direction of the wheel plane. And the component of x dot that's perpendicular to the wheel plane is x dot cosine alpha plus beta. Similarly, the robot's y velocity can be decomposed into two components. We've got this y dot cosine alpha plus beta in the wheel plane direction. And then we have y dot sine alpha plus beta, which is perpendicular to the wheel plane. And then from theta dot, we also have some velocity of this point. So here's theta dot L. We can break that down into parallel and perpendicular components relative to the wheel plane. So what we can say is that if we add up all these velocity components that are in the direction of the wheel plane, they have to add up, or they're equal to r times phi dot. So this theta dot times L cosine beta, this x dot sine alpha plus beta, and y dot times cosine alpha plus beta. All those add up to r phi dot. And then the sum of all the velocity components perpendicular to the wheel plane, they add up to zero. So this velocity plus this velocity plus this velocity add up to zero. Introducing this notation, I dot r is the velocity in the robot frame. So we have x dot r, y dot r, and theta dot. And here is the equation for the rolling constraint. So we've got x dot, and it's in linear algebra form. So we have x dot r times sine alpha plus beta. So there's that parallel component. And we have minus y dot r cosine alpha plus beta. There's this component. And then we have theta dot L cosine beta. So there's that component. And those all add up to r phi dot. And then the no sliding constraint, which is that the velocity perpendicular to the wheel is zero. X dot r cosine alpha plus beta is this term. Y dot r sine alpha plus beta. And theta dot L times sine beta. So all those add up to zero. So there are two constraints for the standard wheel, the rolling constraint and the no sliding constraint. And so we can do this for any of the four wheel types that we looked at in the previous video. Here's an example of using the rolling constraint. In this example, we have a robot where alpha is 0 and beta is 0. And so that would be the wheel would be at this position relative to the robot frame. So here's the equation from the previous slide of the no sliding constraint. And whenever we plug in these values for alpha and beta, we get this equation. And all that boils down to is that x dot r equals 0. So it's saying that the x component in the robot frame of the velocity is 0. So we're not moving perpendicular to the wheel plane. So that mathematically is just what we're saying. Now, to find out, we want to find out the kinematic constraints for the robot chassis, because we want to be able to express the robot velocity in terms of the wheel speeds. And the way we can get the constraint equations for the entire robot is just to sum up the contributions of all the different wheels. So each wheel imposes 0 or more constraints on robot motion. The fixed standard wheel imposes 2 constraints, the rolling constraint and the no sliding constraint. What about, say, a spherical wheel, a non-powered spherical wheel? What constraints would that apply? Well, if it's non-powered, that applies no constraints on the robot motion. So however the robot wanted to move, the spherical wheel velocities could account for that. Say we have M standard wheels here, and we want to figure out what the constraints are on the robot chassis from all those wheels. We can just combine them all like this. So we have the rolling constraint equation for each wheel, and each wheel gets a row in these matrices. So here are the terms locating each wheel, alpha and beta and L, for each of the M wheels. And then this diagonal matrix is just the radius of each wheel. And then we have a vector with the speed of each wheel. And so that was just writing this equation for all M wheels and then stacking it. And so instead of these matrices, we'll introduce this notation. So this matrix we're going to call C sub P, and then psi dot R we introduced in the previous slide. The matrix of the wheel radii is W, and then the vector of the wheel speeds is phi dot. So you can see the difference. This is a bold symbol, and this is not bold. So bold implies that, or indicates that it's a vector. So CP and W are matrices, and then psi dot and phi dot are vectors. So psi dot and phi dot are in bold. Now we do the same thing with the no sliding constraint. So we just have the no sliding constraint for all M wheels. And then we end up with this equation. So this matrix is C sub N, and then psi dot R. And that product is equal to 0. Because the motion perpendicular to each wheel is 0. Now we're going to look at the differential drive robot. And before we do that, let's talk about coordinate transformation, because we often want to define or set the velocity of the robot in the world frame. So we care less about the velocity in the robot coordinate system than we do in the world coordinate system. And it's a simple rotation matrix that will transform from the world coordinate frame to the robot frame. And that matrix we're calling R. And here's the definition of it. So it's just dependent on the angle theta. And if we want to go from the robot frame to the inertial frame, then we just invert R. So our kinematic constraints earlier, we wrote them in terms of psi.r. For example, in this case, the robot can go forward in the x sub r direction, and then it can't move its velocity in the y sub r direction 0. And then, but from now on, we're going to work with the inertial frame. So instead of psi.r, we'll see r times psi.i. And one other point about this differential drive robot, we've got two fixed standard wheels. So we'll have constraints from those wheels, two constraints from each wheel. And then here we have a spherical wheel or a caster wheel. This is a passive wheel and it adds no constraints to the robot, so we can ignore that one. For this robot, we will combine the no slip and rolling constraints to yield this equation. So we have the product of C sub P stacked with C sub N, multiplying that by the rotation matrix times psi dot I. And this product here, R times psi dot I, is just the velocity in the robot frame. And that's equal to this stacked or block matrix. We have W times phi dot and then 0. So the zeros would, this should be a vector here, a vector of zeros. Okay, for this example, we have these parameters. Alpha 1 is negative pi by 2. So that means that we have one wheel down here on the y-axis. And beta 1 is pi. And the reason beta 1 is pi is so that a positive velocity, phi 1, will give us a robot velocity in the positive x direction. And then for wheel 2, we have alpha 2 is pi by 2, so that wheel also is on the y-axis, and beta 2 is 0. So we can see that just by rotating this wheel up to here and setting beta equal to 0. And then both wheels are the same distance from the origin, so L1 is L2, we'll just call that L. And both wheels have the same radius, so R1 is equals R2, we'll just call that R. If we take these values and substitute them into this equation, then we get this. So here are the two lines, rows from the rolling constraint. Substituting alpha and beta and L into that equation will give us these values. And then we have R times phi dot 1, R times phi dot 2. And then the last two rows are from the no sliding constraint. And you can see that these last two rows are redundant, so we really only need one of them. The fourth or the second no sliding constraint doesn't add anything. So you can see that intuitively, say this wheel 1 keeps the robot from moving in the robot Y direction. Well, wheel 2 doesn't do anything in addition to that. So it also keeps the robot from moving in the robot Y direction, but we already had that constraint from wheel 1, so we don't really need this fourth row here. So because it's redundant, we'll eliminate that equation. And now we have a full rank matrix. And so we can use this equation to perform kinematics problems. So if we want to solve the forward kinematics problem, that's where we're given the wheel speeds and we want to find the global velocity, then we can rearrange this equation to find psi dot I in terms of phi dot. So that just looks, we invert this matrix, multiply it, invert the rotation matrix, and multiply that there too. And so the inverse of this matrix looks like this. And here is our equation giving us the velocity in the inertial frame in terms of the angle theta and the wheel speeds. So if you were to multiply both sides of this equation by r, then we would have r times psi dot I, and then we would just have these terms here on the right-hand side. And R times psi dot I, what is that again? That's psi dot R. So the product of R and this vector is the speed in the robot frame. So if we just look at these two matrices, the product of these two matrices is the velocity in the robot frame. And what we're saying here is that x dot is equal to r times phi1 over 2 plus r times phi2 over 2. So that's saying the velocity of the robot in its x direction has a contribution from each wheel. Y dot is the second row, so y dot is equal to 0. So that's the y dot r. So the velocity in the robot y direction is 0. So that is the contribution from the second row, or that's the constraint applied by the second row. And then theta dot is the difference between 1/2 r phi dot 1 and 1/2 r phi dot 2. So for example, if phi1 dot is equal to phi2 dot, then the robot has a certain value for x dot in its local frame, y dot is 0, and theta dot is 0, because these two terms cancel out. And if phi1 dot is negative phi2 dot, then x dot is 0, because those terms cancel out. And the robot is just spinning in place. So theta dot is r phi1 dot plus r phi2 dot. Inverse kinematics we can also solve with this equation here, except we'll only take the top two rows. So inverse kinematics, that's where we want to find the wheel speeds given a global velocity. So here we're given psi dot I, and we want to find out what wheel speeds we need to set in order to have that velocity. And so this is that the top two rows of this equation rearranged. Phi dot is the inverse of W times CP times R times psi dot I. Well, I know this is a sort of long video, but there is a lot of information that we covered about the kinematics for a wheel. And the idea is that each wheel is going to limit the robot velocity in some way. So the rolling constraint means that the robot velocity in the wheel plane direction has to be equal to the product of the wheel radius and its speed. And the no slip constraint means that the robot velocity perpendicular to the wheel plane direction has to be 0, because the wheel isn't slipping perpendicular to its wheel plane. And then we can just combine the contribution from all the wheels to get the constraint equations for the robot chassis. And once we have those equations, the independent equations, so if there are redundant constraints, we remove those. Once we have all the independent constraint equations, then we can use that to solve the forward and inverse kinematics problems. Forward is where we're given the wheel speeds and we want to find the global velocity. Inverse is where we're given the global velocity and we want to find the wheel speeds.